And let's try an example of using the Ampere's law to calculate the magnetic field of a certain case. And we will, of course, try the simplest example. The simplest example is the case of a straight wire whose cross-section is circular. Okay. And then if you look down along this wire, it will look like this. So here we have a circular wire, and the current is coming out. And then we want to know the magnetic field. First outside of this wire, and then later inside the wire. First, if you want to calculate the magnetic field outside this wire using Ampere's law, then you first have to set up the Amperian loop. And for the simplicity of the calculation, you have to set up the Amperian loop so that it will have the simplest shape and the symmetric shape, right? And how would you set up the Amperian loop? Of course, the simplest case will be circular Amperian loop, just like shown here. It's already shown, many of them are shown here. Okay, I will choose, say, this one. And then, assuming I'm drawing a perfect circle, okay, it will go around like this. This is my Amperian loop. And then we will calculate the magnetic field. Here, let's set up the radius of this Amperian loop is, I will use a symbol small r, and then it is larger than the large R, which is the radius of this wire. Okay, it's large R. Okay, so let's use the Ampere's law. So we first have to calculate the magnetic field and its integration around this Amperian loop. And then if everything is symmetric, of course the magnetic field will exactly go tangential to my circular Amperian loop, right? So therefore, now this magnetic field and then the length vector going around Amperian loop will always be parallel to each other. So therefore, I don't have to use the dot products. I can simply multiply between them. And then, again, if everything is symmetric, the size of the magnetic field will be the same everywhere around this Amperian loop because it is always at the same distance from this current, right? So therefore, B is in fact constant, so it will go to outside the integration. So here we are integrating the small section, small length section along the Amperian loop going around the full loop, right? So if you add them, what you actually get is nothing but the total length of the circumference of this loop, right? So it's a circle with the radius r, so therefore, of course, its circumference will be 2 pi r, right? Okay, so we have completed the integration, and according to the Ampere's law, it is equal to the permeability constant multiplied by the enclosed current. So how much current is enclosed inside this Amperian loop? We already said that this wire carries the current I, right? So I will be the only current inside, right? So then by comparing these two sides, we can finally write that magnetic field is equal to the permeability constant. Permittivity constant. Permittivity constant multiplied by the current divided by 2 pi r. Does it look the same when you compare with the result that we obtained from the Biot-Savart's law? Of course, they look the same. Okay. Well, we use a little bit different symbols sometimes, but what they mean is exactly the same. So whichever law you may be using, the physics has to be the same. Okay, good. And then how about the current inside the wire? Okay, now if you are inside the wire, for example, this will be your Amperian loop. Okay, in this case, now this small r will be actually smaller than the radius of this wire, right? And in that case, you can immediately see that current enclosed by this loop is in fact must be smaller than I, right? So now the amount of the enclosed current depends on how the current is distributed. And strictly speaking, the figuring out the current distribution inside the wire is not very easy. Most of the time, the current flows along the surface, but some of them are distributed inside. So quite often it's very difficult. But just for the sake of simple calculation, here we will just assume that current is uniformly distributed. Okay, then that will make the calculation simpler, because here we are only trying to figure out how to use Ampere's law, right? Okay. Then how about the integration of the magnetic field? It's actually exactly the same as what we have done above. So it will be simply B multiplied by 2 pi R, and what is only changing is the amount of the enclosed current. And since we have assumed that current density is uniform, now the actual amount of current is proportional to the size of the area, right? So therefore, starting from the total current, we have to divide it by the total area of the wire, and then multiply it by the total area of the Amperian loop. So multiply by 2 pi, multiply by pi small r square, and divide it by pi large R square. So, and then here we have R square here, and then here we have 1 R. So therefore, if you finally summarize it, your magnetic field will be proportional to R. Okay, so now we get different results depending on whether you are inside the wire or outside the wire, and then you can draw the result using a graph together, right? So inside the wire, now the magnetic field is proportional to the distance so it's straight, is increasing, and then as soon as you reach the surface of the wire, and then if you go to a larger distance, it will decrease following the inverse proportionality of the distance. Okay. So, so far we have discussed both Biot-Savart law and Ampere's law. Okay, and then, they are shown here using mathematical equations. I hope you understood them all and then remember well. And here I think I have to mention one thing in order to avoid confusion. Here, when I was writing these two laws, I was of course following the convention of the symbols given by the textbook. Okay, and there may be something you might be confused, so let me point it out. Both of these laws or integrals includes this ds factor here. Actually, in the Biot-Savart law, ds here, and in the Ampere's law, ds here. And then this ds factor is slightly different between these two laws. And of course, in both cases, ds factor is a kind of length factor. Its length factor is following a certain curve. But in the case of Biot-Savart's law, this length factor follows the current, right? So here, since the current cannot be a vector, so instead, ds was used in order to represent the direction of the current, at the same time the length of the wire, right? But then, in the case of Ampere's law, this ds does not follow the current, right? So even though you have a current here and there in the Ampere's law, never think that ds follows this current. ds in the Ampere's law is in fact following the Amperian loop, right? So direction of the ds is not directly related with the direction of the current, but it depends on how you set up your Amperian loop, right? Okay, so I hope you already understood it, but if you somehow have not yet realized it, please remember this ds factor is different between the Biot-Savart's law and the Ampere's law. Okay. And one more time, let me compare between the equations for electric fields and those for magnetic fields, because this is very important. Okay, so in this table, we have compared these three equations from each side. And first, let's compare between the differential field, how we calculate the differential field. For the electric field, is given by the Coulomb's law. So that's ds vector, which is a small portion of the electric field vector coming from the small portion of the electric charge, is given in this way. And if you integrate this properly around the charge distribution, then you will be able to get the full value of the electric field. Okay, and then the counterpart for magnetic field is given by the Biot-Savart law. So here the dB vector, which is the small portion of the magnetic field vector coming from the current carrying wire ds vector, is given in this form. And of course, again, if you properly integrate this around, integrate this over the current distribution, then you will be able to calculate the full value of the magnetic field. Okay, so these are more or less like general formulas, but there are convenient laws which involve the integrated flux. So in the case of electric field, is given by the Gauss law. So what it says is that if you integrate electric field over a closed surface, which we call Gaussian surface, then you will get the value proportional to the total amount of enclosed charge inside this Gaussian surface. And the counterpart for the magnetic field is given by the Ampere's law. So here, if you integrate the magnetic field going around a closed loop, which we called Amperian loop, then you will get the value proportional to the total amount of enclosed current, which is enclosed by this Amperian loop. Okay, and then also remember that in the case of Gauss law, the proportionality constant was the inverse of this electric permittivity constant. And in the case of magnetic field, the Ampere's law, the proportionality constant was the magnetic permeability constant. Okay, so I think in one of the slides, I kind of mixed between the permittivity constant and permeability constant. It's very confusing, right? But let me make a correction that for the magnetic field, it is permeability constant, and for the electric field, it is permittivity constant. Okay, I'm sorry for the confusion, but I just made a correction here. Okay, and then lastly, for the force given acting on charge or current for the electric field, now the electric force or the Coulomb force is given as the charge multiplied by the electric field acting on it. So therefore, in this case, the direction of the force is either parallel or anti-parallel to the electric field, depending on the sign of the electric charge, right? But in the case of magnetic field, it is very important that the electric charge has to move. So we need the velocity vector. So if you multiply the charge and the velocity vector by the cross product with the magnetic field, then you will get the magnetic force. Okay, and then the charge moving actually implies that there may be a current. So you can also write the equivalent form using the current multiplied by the length vector cross producted by the magnetic field vector. Okay, so here important thing is that for the magnetic force, it is not parallel to the magnetic field, but it has to be perpendicular to the magnetic field. Okay, so make sure you remember them and understand them. Okay.